Hello. This is me explaining basically the second half of the homework for Unit 2. So we're going to start with 3.11, the instantaneous vector velocity. So this is basically one question per assignment, per section. So the question that we're going to do for 3.11 is question 2.7. It asks, a car is stopped at a traffic light. It then travels along a straight road such that its distance from the light is given by x of t is equal to bt squared minus, I don't know if you can see that, minus ct cubed, where b is equal to 2.4 meters per second squared, and c is equal to 0.12 meters per second cubed. It's asking, first calculate the average velocity of the car for the time interval t0 to t 10 seconds. So we're going to do that one first. So basically, you're given this equation and you're given values to plug into the equation. So it's more complicated than it actually is. So once you plug in the values, your equation is literally just going to be this. It's going to be x of t is equal to, this was going to be b originally, but it's 2.4. And this was c originally, but it's 0.12. So this is your equation. So your first question is asking you, find the average velocity for the time period between t equals 0 to t equals 10. So 10 minus 0, like delta t, is literally just going to be 10. Because you'd start at 0. So your change in time is going to be 10. So first, you have to find what the x was when t was 0. So x of 0 when t was 0 is just 0. If you plugged it in, if you plugged in 0 for t, you were going to get 0. And then if you plug in 10 for the value of x, you plug in 10 to where all the t's are, and you get 2.4 times 10 squared minus 0.12 times 10 to the cubed. You get, you get your delta t is equal to 120. So when you find the v average, you know that the average velocity is equal to delta x over delta t. So your delta t, you know, is 10. Your delta x, it's 120 minus 0. It's going to just be 120. Your change in your average velocity is going to be 12 meters per second. Now for part B, it's asking you calculate the instantaneous velocity of the car at t equals 0, t equals 5 seconds, and t equals 10 seconds. So the instantaneous velocity sounds complicated. It's not really that complicated. So we're just going to do the first kind of section of this problem. The instantaneous velocity, it looks complicated. It's not really. So let's do it for t equals 0 first. So the formula for the instantaneous velocity is the limit as t approaches 0 of delta x over delta t. Now, limits are used in calculus, but that's just basically to say that you're trying to get delta t to equal 0 as close as you can get it. So the difference of delta t is very, very, very small. So when your time is given to you and you're having to find the instantaneous velocity, you can pick your time value and a value that is very, very close to it. So if my t is like, okay, find the instantaneous velocity at t equals 0, I can have this be t1, and then I can choose t2 to be something very, very close. So 0.001, right? Which means that my t1 minus t2 for my delta t at the bottom here is 0.001 minus 0. So that's how close I want it to be. And the logic behind that is when you're finding the instantaneous velocity, you're trying to find a very, very, very small section, right? If your velocity, for example, is like a chart and it's like t velocity, and you're like, boom, okay. Basically what you're trying to do is instead of trying to find like velocity at like t1, t2, trying to find this, you're trying to find of 1 point of just 1 t. And that's kind of impossible unless you take a tiny, tiny, tiny point, like very, very close to it, almost invisibly small. So this t in our example is actually t equals 0. And we can show that by doing this, is t equals 0. And then the other value that we made up is t equals 0.001. It's very close. It's not given in the problem to find t.0001. We made that up so that we can find a value close to t equals 0. So to do the top half of this equation, you have to find the change in x. And you can only do that if you have a, if you plug in x of t is equal to what your t's are, right? So your t1 is 0. So that's x of 0 over here. And your t2 is 0.001 that you made up. So you find that one over here. Now, I just put it all in the top half of this equation so that it kind of made more sense to me, but you don't have to do that. You can do it separately off to the side. And I plugged in the values of my equation up here. I plugged in all of this, and then I plugged in my values for t. So this is 2.4 times 0.001 squared minus 0.12 times 0.001 cubed, and this is all your x2. And then this is your x1, because you're finding the value of t1. X of t1, which is equal to 0. So this is basically just going to become 0. Like, we don't care about that. And you end up with this. And, you know, because it's minus 0, you don't really have to, it's unnecessary to include that. And then when you do the math, your instantaneous velocity at t equals 0 is equal to 0.0024. And literally just repeat that process for all the ones at the bottom here. So I was given the values of t equals 0, t equals 5, and t equals 10. We see that over here. So in order to find t equals 5 instantaneous velocity, it's literally the same thing. You plug in your x1 over here, and this is your x2. And your x of t1 is over here. That's t1. And this is your t2 that you made up. And that's it. You just repeat the whole thing. You just solve for the different values of x using the equation that you have. And then at the end, you get the velocity of instantaneous at t equals 5 is 15. And the velocity instantaneous at t equals 10 is all the way over here. It's basically 12. And yeah, that's it for that one. Oops. Okay, so moving on. The equations of motion. There's the problem that's given to us is in the fastest measured tennis serve, the ball left the racket at 73.14 meters per second. A served tennis ball is typically in contact with the racket for 30 meters per second and starts from rest. Assume constant acceleration. A, what was the ball's acceleration during the serve? B, how far did the ball travel during the serve? So if I look at this question, I already have these values. I have the value of, oh, I can't write on that one. Okay, I have the value of here, this is the velocity. The ball left the racket at this. This is V initial, 73.14. I can write that a bit bigger. Excuse me. So V initial is 73.14. A served tennis ball is in contact with the racket for 30 it's not microseconds, 30 milliseconds, and starts from rest. So your value for delta t, you have to convert milliseconds to seconds. So that's done for us over here. So 30 milliseconds is equal to 0.03 seconds. That's over here. Sorry if the paper is kind of dark. So ball left the racket at, okay. So we're assuming constant acceleration. So acceleration is constant. Okay. Yes, okay. So actually, my mistake. So we're not using the 73.14 as the initial. We're using it as V2 because when you're looking at this problem, this is basically what they're asking. The speed at which it left the racket is 73.14 meters per second, and the speed that it was originally on the racket is 0. So this is what they are, the situation that they're referencing basically. And it does this over a period of time of 0.03 seconds. So we're asking, what's the ball's acceleration? So that's pretty easy. So we know that if it starts at 0, then the delta v is going to be the same value as the second velocity that we have. So the delta v is 73.14, because if you imagine it, it's minus 0, it's still going to be 73.14. So you can easily solve for acceleration by plugging it into the equation for acceleration. So if I plugged in my value for delta v here and my value for delta t here, I have this value, meters per second squared. And then part B, it's asking, my mistake, how far did the ball travel during the serve? So you're solving for delta x this time. So we're going to use this equation here. So this equation is an equation that includes the values of v final, v initial, the acceleration, and delta x. Usually you don't have to write the acceleration as ax. You can just probably leave it as a and you like use it circumstantially, but it's helpful to know ax in this situation. So we already solved for ax. We know that our value for a is the thing that we just solved for, which is this. So we can plug that in. And then we know that our value for v final is what is given. And we know that v initial is 0, so we can cut that out immediately. So after plugging everything in, we're just solving for delta x, and delta x is equal to 1.097 meters. And that is that problem. That is 2.22 for 3.12. Okay. So 3.13, for freely falling bodies, we're going to do 2.36. So this problem is, a small rock is thrown vertically upward with a speed of 22 meters per second from the edge of the roof of a 30-meter tall building. The rock does not hit the building on the way back down and lands on the street below. Ignore air resistance. A, what is the speed of the rock right before it hits the street? So we're going to do A first. So our data, basically, we can visualize this as this little visual over here. So it's thrown from the ledge of a building. Your rock is thrown from the ledge of a building. It goes up, and then it comes back down. So you have your initial point, which is point A, your kind of middle point, which is point B, and then your bottom point, which is point C. So if it's thrown vertically at 22 meters per second from this 30-meter tall building, we know that our V initial is 22 meters per second. Our final position is going to be delta y minus 30 meters. Y minus, well, our A initial is this level right here, and it's going to end up at the bottom here. So if you think of this as like a y-axis, and an x-axis, this is going to go down 30 meters. It's not going to be level with the start, with the initial height. It's going to decrease by 30 meters total because that's the height of the building. So, yep. So we know that our final position is a change of y of negative 30 meters. So we're looking for the final velocity, the velocity at which it almost barely hits the ground. So we can use the equation vf squared equals v initial squared plus 2 acceleration of the change in y. Now this equation, we just used it for the change in x. It can also be used for the change in y. It literally just depends. So technically this is vfy, and technically this is voy, this is ay, right? This equation, you can use it for the x or the y-axis, it doesn't matter. So when I plug it in, I get the values of the initial, I can plug in right here, this is 22. The acceleration is just gravity. Now, it's very useful to know, so this is a distinction that should be made. Acceleration is a vector that is equal to negative gravity. And gravity is just 9.81 meters per second squared. So I always separate these two in my brain. So it's important to know that whenever you're using the AY, it's negative 9.81 and not positive 9.81. And whenever you're plugging in just for G and you're not plugging it in as acceleration, it's going to be positive 9.81. So this, because it's AY, I can safely assume that it's going to be negative. So I can plug in negative 9.81. And then the change in Y, I plug in negative 30. And when I solve for it, because this is VF squared, ultimately I have to square root everything. And then I get VF is equal to, right here. VF is equal to negative 35 meters per second, and it's negative because it's decreasing, it's going down. Kind of literally, it's going down. The second part of the problem is asking, if I'm not mistaken, how much time elapses from when the rock is thrown until it hits the street. Okay, so the time that elapses, so now we're solving for the change in t. So delta t, I can solve using this formula, VF is equal to V initial plus A delta t. I can kind of rationalize this equation as V final is equal to V initial plus delta V, and delta V is the same thing as acceleration by the change in time. So I can just plug in the value of VF that I just created. So this is the value that I just created. I plug in VO, I plug in acceleration, which is the negative gravity, and then I plug in, I'm solving for the change in t. So I just, calculate it all the way through with algebra, and then the change in t is equal to 5.58 seconds. And that's that problem. Parabolic trajectory is a little bit more complicated, but it's not too bad. So this problem is asking, excuse me. This problem is asking a daring 510N swimmer dives off a cliff with a running horizontal leap, as shown in this figure. What must her minimum speed be just as she leaves the top of the cliff so that she will miss the ledge at the bottom, which is 1.75 meters wide and 9 meters below the top of the cliff? So this is worded weirdly, but the principle of it is pretty simple actually, because it's literally just finding the velocity initial given a delta x this right here is a delta x and given a delta y, right? So this delta y value is technically negative because she's going down. So if I go to solve it, okay. So we know our delta x. I left, in this problem, I left the delta y positive because I arbitrarily, like, ultimately the velocity should have been, I believe, negative because she is going down. But, you know, the math checks out. So I know that in order to solve for the speed of v initial, I cannot use any equation that doesn't also have an unknown t. So first of all, I need to solve for my unknown t. So thankfully, I have a formula that I can helpfully use, which is this formula right here, which is derived from other formulas. And it basically says that your t is equal to the square root of 2 times the change in y over acceleration. So this would be acceleration of the y-axis. So this would be gravity, negative gravity. So I plug in my value for the change in y. So this is delta y, and this is okay, yeah. So you see how I made an error initially. So this should be negative, and this should also be negative, such that they cancel out, and you can have a positive beneath this equation. I just sort of like, it was my error. I forgot it, but it ended up being correct anyways. Just because I, forgot it. So once I know the change of t, this is technically delta t, but since t initial is 0, you can just sort of consider this is t final, which is why I'm not putting the delta symbol all the time. So now that I know t, I have to find v initial. So we know that the equation of x is equal to x equals v times delta t. And technically this could be considered delta x, and it can also be considered x final, and it can be considered x at the value of t. It's up to you how you define it. And when I go to plug it in, I understand that the velocity that I'm solving for is this one right here. I know my value of x final, and I know my value of delta t. So when I plug them in, this could be considered delta x, this could be considered vx, this could be considered delta t, could also be considered the change in vx. It's all just sort of like, it all comes out in the wash in this problem. So when I plug in everything, I get the velocity is equal to 1.29 meters per second. Technically, I believe, if I'm not mistaken, I believe this should have been actually negative 1.29 meters per second. But the math is the same. Okay, circular motion. This one's pretty easy. A Ferris wheel with a radius 14 meters is turning around a horizontal axis through its center. The linear speed of a passenger on the rim is constant and equal to 6 meters per second. What are the magnitude and direction of the passenger's acceleration as she passes through A, the lowest point in her circular motion, B, the highest point in her circular motion, and C, how much time does it take the Ferris wheel to make one revolution? Okay, so we know that the radius is equal to 14 meters, and we know that the velocity is equal to 6 meters per second. So I have to find the magnitude and direction of acceleration. And when it comes to circular motion, this equation holds true. This equation right here. Acceleration is equal to volume, wow. Velocity squared over radius like that. In this problem, it's negative because it's asking as the acceleration, I believe, goes down and then goes back up. So it starts, we were considering it negative just in this problem, but if it was going up, it would be positive. So that's why that negative symbol is there. It's not there all the time. It's just for this problem. So we have the values for v and r, so we just literally plug them in. And this is what we have for acceleration. And the A is asking for what is the acceleration at the lowest point. So at the lowest point, it has nowhere to go but up. So this acceleration is positive. And at the highest point, it has nowhere to go but down. So the acceleration is negative. So it's the same value the entire time. But at the lowest point, it's positive, and at the tallest point, it's negative. And then it's asking to find the time it takes to do a full revolution. So the other equation that we use is this equation here, which is the magnitude of the velocity in circular motion is equal to 2 pi r over delta t. And 2 pi r is the same thing as d. It's also the same thing as delta x. It's just like the distance that it travels. So we actually know the variables that could be able to solve for this distance thing here. And we can use this to our advantage because this includes delta t with the variables that we know, and we can solve for delta t without actually having to use this full equation over here. So this is equal to technically delta x. It's the same thing. So I know the values that can be plugged in for this top equation. So I know r, and I know the velocity. So I just plug them in, and then I get delta t is equal to 14.66 seconds. So this is like just a matter of knowing which way to mess with your equation so that you can plug in the variables that you know. So originally, I don't actually know delta x, right? This is not something I know, but I know that delta x in this situation is equal to d is equal to 2 pi r. It's not too freaky. Okay. Next one, and we're almost finishing up here. This is a problem that was written specifically by the professor. So it's under orbit of an Earth satellite for 3.17. So the moon's orbit around Earth is a period of 28 days. And we know that the radius is 350,000 kilometers. So we can find the acceleration or the gravity of the moon's orbit around Earth with these variables pretty easily. So the first thing we do is literally just convert the kilometers to meters, and then we also convert 28 days to seconds to get the units to work out in our equation. So we know that there's 1,000 meters in a kilometer. We convert it to 3.5 times 10 to the power of 8 meters. That's a lot of meters. And then we know that 28 days is, within 28 days, there's 24 hours. Within 24 hours, there's 60 minutes in an hour. And within each minute, there's 60 seconds. So if I multiply it straight through, we have a lot of seconds. We have, I believe it's 2,419,200 seconds. So once we know that the equation for acceleration is the change in velocity over time, and we know that if we just do it all the way through, it's also equal to 2 pi r over t. So this is an equation specific to circular motion. It's like specific to the stuff that we were just doing. So if you plug everything in, you just get this. It's equal to 909.02 meters per second squared. So almost like 1,000, almost 1,000 meters per second squared is the acceleration here. The conical pendulum is a similar instance of just being given data and finding the period and finding the velocity. So the data that we're given is over here actually. So we're given that in a conical pendulum, which looks like this, and then forgive my handwriting. We're given this is, I believe this would be 30, and our length is 1 meter, and the gravity is obviously going to be 9.8. So using this data, we have to find first the period, and then we have to find the velocity. So first part of the problem is over here. This equation is something that we know is specific for conical pendulum. So specifically for conical pendulum, we know that the period can be solved for, this is the period by the way, period is big T. Period can be solved for using the equation of 2 pi multiplied by the square root of the length times the cosine of theta over gravity. So if I plug that in, I know what the length is. The length is right here. I know what the angle is. The angle's right here. I know what gravity is. So once I plug that in, I get t. And then the velocity is the second part of the problem, and it can be solved with knowing that and this is also specific to conical pendulum. It can be solved knowing that the velocity squared is equal to the radius times gravity, which is equal to 2 pi r squared over t squared. So we don't really need this part of the equation. We can use, and this is specific to conical pendulum, we can use this equation to solve for r. So we know the length is literally just 1, and we know that the angle is literally just 30. So once everything is plugged in, we know that r is 0.5. So the equation becomes 0.5 times 9.8, and this is squared to begin with, so we have to find the square root of both sides to cancel out this square root. So your velocity becomes 2.21 meters per second. And it's pretty self-explanatory, pretty easy. Our last problem, yay, is for Galilean transformation. This is 3.32 in the book. So let's see what the actual problem says. So it says there's 2 piers, and they're located on a river. So B is 1,500 meters downstream from A. B is over here. This is B. B's right there. And 2 friends must make round trips from pier A to pier B and return. So one of them rows a boat at a constant speed of 4 kilometers per hour relative to the water. So this boat is 4 kilometers per hour. And the other is walking on shore. Let's pretend that there's a guy right here. And his speed is 4 kilometers per hour as well. The velocity of the river is another thing that we have to account for, and the velocity of the river is 2.8 kilometers per hour in the direction from A to B. So the velocity of the river is helping this little boat. How much time does it take each person to make the round trip? So if we think about it, this little man, he's not dealing with the velocity of the river. So he is going to travel this entire length at 4 kilometers per hour and then back at 4 kilometers per hour. However, the boat, despite the boat's velocity being 4 kilometers per hour, it's also dealing with the river. So it's going to take less time to travel from A to B because the river is helping it, but it's going to take more time to travel back because the river is going against it. So let's look at what that looks like in math. So relative velocities and Galilean transformation, it's all kind of fussy. So firstly, we do this conversion. We have to convert for everything in the same units, and it's just easier when everything is already in kilometers per hour. So we convert the distance of the length of the river from 1,500 meters to 1.5 kilometers. So this is just my recreation of exactly what we just did. So first, let's calculate for how the man walks. So we can use this equation because we're going to have to calculate for the time, and it's fairly easy to calculate for the time because we know everything else that the man is dealing with. So the equation is actually the same thing as this one over here, because delta x is the same thing as the velocity by the change in time. And we have to solve for time, so the time has to be somewhere in this equation. So we know the value of x of t. This is the same thing as x of final, which is the, which is the same thing as the delta x in this situation, because you start from zero, right? So your delta x is equal to 1.5, because this is the kilometers, the length of the river. So I plugged this in here. The x initial, you start from the origin, so it's just 0. And your velocity, the velocity that the man is using to walk, is 4 meters per second, and it's not affected by anything. So this is the straightforward equation. So the change in time is 0.375 hours, I think. And this is just from A to B. Now we're going to do from B to A. So this is B to A. This is in reverse. This is the man walking back to the origin. It's the same exact thing because the man is not dealing with the river. So the man has to travel 0.375 hours times 2. So the total time that the man takes is 0.75 hours. And I can calculate how many minutes that is. I believe it can be done by doing 0.75 divided by, oh geez. Hold on, 0.75. Yes, okay. Times, yeah, just times 60, because there's 60 minutes in an hour, and then you get 45 minutes. Okay. So that's pretty explanatory. So now we're going to do the boat. The boat's math is over here. This is where the boat's math starts. So the boat, I first do A to B, right? I first do like straight through from A to B. So the velocity of the boat is a little bit more complicated because it's also dealing with the river. So the x of t is equal to, we see here, x of b t, which is like the initial velocity of just the boat. So b is equal to boat. So this is you know, this is the same sort of speed that the man has been walking, right? And then this extra complication is the river. So when we plug it in, the distance of the river is the same. This is the same speed that the man is walking. And then this is the influence of the boat. So thankfully, this is the same variable, so we can add them together. So the change in time from A to B is 0.221 hours. And then from B to A, it's the same exact thing, but it's going against the water. So the water is hindering it. So you subtract it instead. So the velocity of the boat is here. The velocity of the water affecting it is here. So it's minus 2.8. You see how it's the same exact equation, except this one is positive because the water is helping it, and this one is negative because the water is hindering. So ultimately, T is equal to 1.25 hours on the way back. So the total time of the boat is 1.25 plus 0.221. And this is however many hours it is. It's 1.471 hours, but I want it in minutes. So let's do times 60. So the boat takes way longer because it's dealing with the hindrance of the water, and it's going to take 88 minutes to travel the same distance that the man did. So the final answer is that the guy is going to take 45 minutes and the boat is going to take 88 minutes. And that's it. That's all the homework, basically, for Unit 3. I hope this helped in some way. And if you have any questions, feel free to message me. I'm not an expert in this, but I like to think I know what I'm doing. So thank you very much.